Hi, I'm Mr. Gru, and we are going to be talking about homomorphic encryption for Montessori students. Till now, we have seen interactive zero knowledge proofs, and how to, in the second presentation, we saw how to convert interactive zero knowledge proofs into zero knowledge proofs. And then we saw a quick overview of how zero knowledge proofs can be constructed using mathematical constructs. And today, we are going to look at homomorphic encryption. Yep, that's me. I'm evil as anyone can get. Now, what is homomorphic encryption? Homomorphic encryption is the conversion of data into ciphertext that can be analyzed and worked with as if it were still in its original plain text form. Suppose you have some data, let's say the number 10, and you encrypt it and get 703. Now you can perform addition and multiplication on uh, 10, 703 as if you were doing it on 10. So you can perform operations on the encrypted data as if you were performing operations on the unencrypted data. Now, addition, multiplication are the basic building blocks of mathematical operations. You can do subtraction as an inverse of addition, you can do division as an inverse of multiplication, and you can construct complex mathematical operations based on these elementary constructs. So using homomorphic encryption, you will be able to perform complex mathematical operations on the encrypted data without compromising the encryption. You don't have to decrypt it, perform the operation, and encrypt it again, because decrypting something would reveal that secret to the entire world. Now, in mathematics, homomorphic describes transformation of data from one set into another set while preserving relationships between elements in both sets. This term is derived from the Greek word same structure for same structure. Because the data in homomorphic encryption scheme retains the same structure, identical mathematical operations will provide equivalent results regardless of whether the action is performed on encrypted or decrypted data. Now, if an algorithm is additively homomorphic, then adding two encrypted numbers together provides the same result as encrypting the sum of two unencrypted numbers, the same two unencrypted numbers. Similarly, if an algorithm is multiplicatively homomorphic, then multiplying two encrypted numbers with the same key is equivalent to raising the product of plain text to the power of the secret key. This is slightly convoluted because it is a lot of mathematics involved. And by raising to a power, you can add the power. So that's why, but never mind. Now, homomorphic encryption can be either additive or multiplicative, and there is a separate categorization called partially homomorphic, somewhat homomorphic, or fully homomorphic. Now, partially homomorphic encryption is a scheme where a defined operation can be performed infinite times on the encrypted data. These encryption schemes are relatively easy to design. Somewhat homomorphic encryption is basically a scheme where a limited number of addition or multiplication operations are allowed as opposed to an infinite number of one operation. It is more difficult to design a homomorphic encryption system that supports a set of operations than one operation infinite times. Finally, the fully homomorphic encryption, where an infinite number of additions or multiplications for encrypted data is enabled, and programs or for any functionality can be run on encrypted inputs to produce an encrypted output. Now, what is bootstrapping? Bootstrapping is a generic technique that allows refreshing encrypted data. It therefore enables one to turn leveled homomorphic encryption schemes into fully homomorphic encryption schemes, and so to make them evaluate any possible function on encrypted data. Now, what is a leveled homomorphic encryption scheme? Let's say you kept on adding to encrypted data and after a certain number of operations, you overflow the buffers. The encrypted values are so big that you can't add them together anymore, or you introduce noise into the operations by every time you encrypt, perform an operation on the encrypted data. In such a case, you will have to do what is called bootstrapping, which is a refreshing technique. Now, fully homomorphic encryption enables arbitrary computation on encrypted data. Now, since Gentry's construction in 2009, several fully homomorphic encryption schemes have been constructed, almost all of which adhere to the following template. Usually, the fully homomorphic scheme that is constructed starts from somewhat homomorphic encryption of some form, and which allows homomorphic computations of some bounded depth. Now, this depth or the number or a limit on the number of operations arises due to some internal noise that gets generated and grows under homomorphic operations. Yet, we have to control this noise, otherwise, we will get an incorrect answer. Therefore, we use this somewhat homomorphic scheme and we convert it into a fully homomorphic scheme by incorporating a refreshing procedure that reduces the noise in the given ciphertext or in the encrypted values by after a certain period. So periodically we run this bootstrapping procedure so that it reduces the noise or the errors in the uh, encrypted values. This refreshing procedure is known as bootstrapping because it uses somewhat homomorphic encryption to homomorphically evaluates its own decryption function. Now you won't understand this part, but never mind. In this bootstrapping process, the function that uh, is used to decrypt the homomorphic encryption scheme is used inside bootstrapping to reduce the noise and uh, uh, eliminate errors. Now, because bootstrapping involves a lot of homomorphic computation and all fully homomorphic schemes depend on it, it must be run very frequently, and it is the biggest bottleneck by far in all known fully homomorphic constructions. Now, these are some examples of partially homomorphic encryption schemes. I'm not going to read them out to you. You can refer to them later. Now, under the fully homomorphic schemes is what is called ring learning with errors problem. Ring learning with errors problem is a very hard mathematical problem related to high dimensional lattices. And based on ring learning with errors, there have been constructed a couple of fully homomorphic encryption schemes. Usually, all of FHE schemes use ring learning with errors. BGV, BFV, CKKS, FHEW, and TFHE, which is an improved form of FHEW. Now, there are a lot of open source implementations of fully homomorphic encryption. Microsoft Seal, OpenFHE, Palisade, HELib, which are available. But whatever said and done, what is the status of homomorphic encryption after 30, 50 years of research and development? See, 30, 40 years ago, homomorphic encryption performed mathematical operations on encrypted values 100 trillion times slower than performing the same operations on the corresponding, unencrypted values. It was 100 trillion times slower. Today, key generation or a cryptographic key generation runs in 250 milliseconds. Encryption takes 24 milliseconds, whereas decryption takes 15 to 26 milliseconds, depending on whether we are decrypting two or three, values. Now, homomorphic addition, which is the underlying operation of, homomorphic encryption schemes, takes less than 1 millisecond, whereas homomorphic multiplication takes about 41 milliseconds. Now, if you might think that this is not an issue, but it is actually is. It on a CPU, on a modern microprocessor, it takes less than a nanosecond to do addition or multiplication. Now, if you compare nanoseconds with these millisecond timings, you would realize that homomorphic encryption today has improved by orders of magnitude, but is still a million times slower than performing the same operations on unencrypted data. Which means if you have to design a system to do some processing or search a database or transform some data, etc., which the query, if it takes 1 second on unencrypted data, will take 11.6 days with fully homomorphic encryption. That is the problem. It is a million times slower than what we need. So the conclusion is that homomorphic encryption is useless garbage. It should not be used in any production grade solutions other than mathematical efforts where you have to prove or use it for research. So that is the conclusion, and I told you I was evil, didn't I?